Welcome back, guys. In this video we're going to start a new chapter. This chapter is about hydrographs, and in this video we're just going to solve two problems, and they're going to be pretty quick. Let's start with problem 6.21. It says determine the following from the hydrograph figure 6.42. Have it right here. Determine the lag time L, time to peak, recession time, base time, and the volume of rainfall excess in cubic feet. So I have here a graph that you can find it on your book. It's figure 6.1, and this figure shows pretty much every aspect of a hydrograph. It shows the duration of the rainfall, like the rain, how long is taking. And if you notice here in the x-axis, we have the time in hours from 0 to 60 hours. And it says that the duration is approximate. It will say if we drag this line down, it will be about 5 hours, the duration of the rainfall. So that's how you read it. It also shows you the losses and the quantity in inches. Here it doesn't show you exactly what it is, but this is an interesting graph because they show the rain data in versus the runoff. So even though it rained only during the first 5 hours, the runoff is gonna keep the runoff hydrograph. It starts at the beginning of the duration and it's gonna continue. The water is gonna continue running off even after the storm has stopped. So let's start with the lag time. To solve the lag time, I have the equation here. You need the duration and the time to peak. So the time to peak in our graph here is the time it takes for the hydrograph to reach its highest volume of flow. In our case, it takes 2 hours to get to the value of 40 cubic feet per second. So our time to peak, it will be 2 hours. And now that we have this, and we know that the duration of this storm is 1 hour, I have it here, we can solve for the lag time, which it will be equals to the duration, 1 hour divided by 2, plus time to peak that we already have minus the duration again. And this equation, all it's doing is finding, technically using the SES method, the time to peak will be half of the duration of the rain. So let's say if it lasted 1 hour, so by the 30 minutes up to when it reaches its peak, the runoff reaches its peak. So we need to find the time between here and here, which will be about 1 hour and a half, and that's what we got, 1.5 hours. And that's all it's doing, this equation, half of the duration plus time to peak, which is 2 hours, minus the duration. So it's this section here plus half of the duration, 1.5. That's all it's doing. Now the recession time is the time it takes to get from the peak of the runoff to 0. So it will be 7 hours minus 2 hours. That will be 5 hours. Base time is pretty much the whole time of the runoff. It will be 7 hours in our case. And again, you can look into this in your book, into this figure if you want. This is like the base time up to the end of the runoff. In this case, you're assuming that you have a little bit here still coming out through the outlet. Now we need to find the area under the curve, and all that is just getting the area under here. Now just pay attention that you have cubic feet per second, and here you have hours. So you want to convert this to hours as well when you calculate the area. And I'm gonna do it really quickly so I'm not losing time. So we have two triangles. Let's find the area of this triangle first. That's gonna be equals to 1/2 times 40. We need to multiply 40 because that's the highest value there. 40 times 2 hours, right? Yep, times 2, but we need to convert those hours into seconds, so we multiply by 36 times 2 times 3600, and that should give us the area in cubic feet for the first triangle. Now let's close that in parentheses. That's the first triangle. Now let's add up plus the second triangle, and it's going to be a very similar approach. 1/2 times 40 times 40 times, in our case is 7 hours minus 2 is going to be 5 times 3600 to get it into seconds so they can be canceled. Hopefully this gives us the area, and that's right, this is what I got. So this is your answer. This will be the rainfall excess volume in cubic feet. And this is what you need to do for this problem 6.21. For problem 6.24, I actually already have it plotted here. I'm going to explain how you get here. Let me delete it so you guys know how to do it on your own. If you're having trouble, you can follow this video. 6.24, given the following recession length of a streamflow hydrograph, develop the recession equations for flow rate. So all this is asking, if we go back to the previous problem, we need to find the equation of the line of the recession curve, which is once you get to the peak all the way down to when there is no more water running off. So they give us the values and they say here we have the peak, the highest flow, all the way down to 20. So all we need to do is plot that. Let's see, I don't like spreadsheets because I find it harder to do charts, but let's make this. So we have this curve right here. This is from these values, cubic feet per second, the flow versus the hours. But to develop the recession equation curve, you want to plot the y-axis of the flow in a log scale. So once you do a log scale, you're going to notice very distinctively the lines, the different periods of the recession. In our case, we have two very distinctive lines. So all we need to do is find the equation that describes these two lines. And we notice that from 0 to 6 hours, we have a very pretty linear line. And from 6 to 14, we have another one. So to make things a little more visual, let me add labels to that and make this from 0 to 1,000 if you want. Yep. So now we have still these two lines, and the way you create these equations, it's by finding first. Oh, let me close this. Is by using this equation here. So we have this equation 6.8 in the book, and all it's saying is like equation 6.8 is analogous to a storage tank. Look at this image here, losing its water at an exponential rate as shown in this figure. So it's all you're doing, this equation is like finding the flow in an exponential rate. How is the flow? The flow is decreasing at an exponential rate, and this equation translates into this, where Q is the intercept for any segment, and I'm going to explain what that is, and then K is the slope for any segment. In our case, we have two segments, very distinctive. So we need to solve for K, which will be the slope. And to come up with this equation, let's solve for K first. And the way you solve for K is the following. You are going to need the values of, let's do equal log 10 of the first value, in our case is 300, minus log 10 of our last value of this line, which is in our case is 30. And all of that you divide it by the time it takes for that line, the time that represents that line, which it would be 6 minus 0, it would be 6 hours, right? Let's do 6 minus 0 so you know what I'm doing. So now this gives you a slope, but of the logarithm. Remember that this is logarithmic right now, so you wanna take it out of the logarithm. So the way you do that is you multiply that value by the natural log of 10. And that's how you take it out of the log value. And this is your actual slope. Another way to do that is to multiply this value instead of natural log of 10 by multiply it by 2.3, which is the same. Natural log of 10 is equal to 2.3, so you can do both. And now that you have the k value, all you need is q. And q is the value of the intercepts our y-axis. So in our case, it will be 300. So our equation will be 300 e to the negative k, which is 0.384 times t. And this equation will help you find any flow in this line between 0 and 6 at any given time between 0 and 6 hours. So if you plug a value here of any t, you'll get a value of the flow at that time. Now, the same approach you take with the next line. There is just one, let's solve it. So you're gonna do equals log 10. In our case, this is 30 of 30. This is the highest value that represents our line, our second line, minus the log 10 of 20, because it's the last value. All of that divided by the time it is taken is representing this line, which in our case is 14 minus 6. And all we need to do again is multiply this by natural log of 10, and that gives us 0.0507 that you could reduce just to 0.05. And again, we got the k value. Now we need the q. Now the q is the value that intercepts the y-axis. So all you need to do is extend this line, extend it all the way here. Now I don't know exactly how to do this in spreadsheets. I will be able to do in Excel, but I don't know how to do it in a spreadsheet. So you're gonna have to trust me. So the answer is gonna give you, is gonna intercept about a value of 40. So you're gonna use 40 e to the negative k that you found is 0.05 t. And this will be the two equations that will represent each of those recession lines. So yeah, that's how you solve these two problems, and this has been an introduction to hydrographs, and I hope you find this helpful, and good luck solving this problem, and I'll see you in the next video. Bye bye.